Hello. In this video, we're going to start chapter 4, discussing probability. The basic concept of probability. So how is probability used in a statistics class? In statistical means, we use it really as a tool to help with uncertainty. We want to look at what situations are likely and unlikely. And in the previous chapters, we used graphs and numerical measures to describe data sets, which were usually samples. And what we want to talk about is this idea of how often something is happening. And so we can define that by talking about what we call the relative frequency, which is the number of times it happens, or its frequency f, divided by the total number of outcomes. And so where do these things come from when we talk in terms of a probabilistic sense? They come from what we call an experiment. An experiment is a process by which observations or measurements are obtained. So examples are like recording someone's age, tossing a dice, recording an opinion on a poll, or tossing coins in the air. And when we conduct an experiment, these outcomes are what we call events. And so we can say a simple event is an outcome that it is observed on a single repetition of the experiment. So that would be recording an age and getting someone that's 26 years old, tossing a die and seeing a 4, recording some preference opinion and getting no, or if we're going to toss 2 coins, one outcome, a simple event, is tossing one of those 2 coins and getting tails. And so some simple event facts we get are, these basic elements to which all of probability are applied. That's what simple events are. These are the basic fundamental building blocks. One and only one simple event can occur when an experiment is performed, right? They're called simple because all these outcomes are broken down into their fundamental simple parts. So if we're rolling a die, rolling a 1, rolling a 2, a 3, or so on, those are the simple events. We denote simple events typically by the letter E with subscripts for counting. So E1 might be the first simple event, E2 would be the second, and so on. And each simple event we get is assigned some sort of probability that measures how often. The set of all of these simple events of an experiment is what we call the sample space, S. And for an example, if we're going to roll a fair die, we'll call S the sample space, and rolling a die, there are 6 outcomes, which we'll label E1, E2, E3, E4, and E5. And we can just label them very simply where the subscript, that number, represents the probability of rolling, or the outcome of rolling a cake. So E1 is going to be rolling a 1, E2 is rolling a 2, E4 is rolling a 4, and so on. But what if we wanted to do some sort of more complex experiment, right? Rolling a die once is a very simple experiment. What if we want to toss 2 coins, or roll 5 die, or draw 3 cards? And so instead of having a simple event, we can have what we call just a plain old event, and that's a collection of one or more simple events. And we typically use any capital letter to talk about an event, although E is not used because it's already used for simple events. And P we don't use. P is really reserved for the idea of talking about the probability of. We start talking a little bit more about probability functions. So we can do an example of this. Right? If we're going to roll a fair die, A is the event of observing an odd number, and B is the event of observing a number less than 4. We can describe all of the things that are in A, right? If we're rolling a die, the event of observing an odd number, A contains the fact that we occur when we roll a 1, a 3, or 5, and B occurs when we roll a 1, a 2, or 3. right? Each of these are the simple events. This A is what we call an event because it's comprised of these multiple simple events. Some events or some experiments can be generated through stages, and it's going to be helpful to use what we call a tree diagram to represent these simple events. So here is an example of a tree diagram for blood type. This is a kind of a good way to represent the different outcomes of a blood type because there are two stages for blood type. There's the actual lettering like A, B, or O, and then the Rh factor. And splitting it up into a tree like this allows us to completely list all the different type of blood types and then determine whether they're a positive Rh factor or a negative Rh factor. At the ends of all of these branches are the 8 distinct simple events of getting A positive blood, A negative blood, B positive, B negative blood, and so on. So some of the properties we get from tree diagrams when we build them is they really just start from a point, right? We're going to start them from a point here. And one stage branches out from that point to these different simple events. And so we would say, okay, those are the blood types. And then every other stage from here will branch out. And so we can say positive, negative, and so on. So we can fill out a tree diagram from there. We'll be doing more examples of tree diagrams as we move on. Another way to display simple events using kind of multiple types of events is to use what we call a probability table. So if we look at that blood type example, we might along one axis use the blood types and along another axis use the Rh factor. To look at A positive blood, we'll just look at where A and positive intersect. Right? This entry will be where the A positive blood. And typically, the entries will be the actual probabilities. So let's do an example of this. We want to list the sample space for the experiment of flipping a coin 2 times. And we'll do this by drawing a tree diagram. Right? So we start from a point. If I flip a coin once, I get 2 outcomes. I can either get heads or I can get tails. This is from kind of the first flip or one flip. And out from there, I can also get a heads for my second flip or tails for my second flip. Same thing here, heads for my second flip, tails for my second flip. This represents the second flip. And then I can list my 4 simple outcomes, right? Following this branch, this would be getting heads on the first flip, heads on the second flip. So that simple event would be HH. The second simple event would be H tails. The third simple event would be tails heads. And lastly, tails tails. Now that we've looked at the outcomes, let's talk about how often an event A may occur. If we're looking at the probability of an event A, we'll write P of A. That will stand for how likely that event is to occur. One way we can start to measure the probability of an event is to talk about a success. A success is a desired outcome of an experiment. If we're looking for the probability that a team loses a specific game, because that's the desired outcome, we're looking for losses. In that case, we would consider a success to be that team losing a game, right? Oftentimes in mathematics, we have phrases that don't really match our connotation. In this case, a success is a mathematical term. It's not necessarily a good outcome, right? We want to separate our connotation of the word success from the mathematical version of the word success. So we can therefore describe the probability of any event A in terms of successes. if an experiment is performed n times, the probability of A is going to be the number of successes divided by n, the number of ways A can occur divided by the total number of ways the experiment has occurred. And so some basic facts about events: each probability must lie between 0 and 1, right? The probability of any event can't be smaller than 0, nor can it be larger than 1. If we have simple events, right, this only holds true for simple events. If I add up all of the probabilities of my simple events, that sum should be 1, right? That doesn't hold true if I just talk about any old event, especially ones that are made up of multiple simple events, right? This equality only holds true for all simple events in my sample space S. If we know an event can never occur, then we define the probability of that event to be 0. If an event must occur, then we define that probability to be 1. And so if we talk about non-simple events, events that are comprised of multiple simple events, we can still think about any event as the sum of its simple events. So the probability of any event A is equal to the sum of the probabilities of these simple events contained in A, right? So every event we talk about, we can break it down into its simple event categories and add up all those simple events. So where do these probabilities come from? How can we find this? We can estimate it using empirical studies, right? That's how, for example, the probability of weather happens. They look at how similar weather events happened given similar circumstances, and they make predictions based on that. Or we can make common sense estimates based on equally likely events. That is kind of more of the phrase of the way that we will be looking at events, right? A lot of events that we talk about are going to be equally likely. So we can just use kind of simple division to figure this out. So let's look at some examples of this. So let's look at this first example. 3 fair coins are tossed and their outcomes are recorded. We want to find the probability of observing exactly 1 head in these 3 tosses. So we'll let A be the event of observing 1 heads. A, therefore, is either going to be heads, tails, 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 head, tails, or tails, tails, heads, right? These are the only possible outcomes that we could get from observing exactly 1 head out of 3 coins. If any of these were changed, we would increase or decrease the number of heads. So what's the probability of each of these events? Well, we said an event can be made up of all of these simple events. The probability of each of these is going to be 1/8. So the probability of A is going to be 1/8 plus 1/8 plus 1/8, or 3/8. Let's look at our second example. A candy dish contains 1 yellow and 2 red candies. We will close our eyes and select 2 candies one at a time. What's the probability that both candies are red? This, I think, is a good indication of using a tree diagram. If we start to build our tree diagram, we start from a point, and if there are 1 yellow candy and 2 red candies, we can say that there's yellow, there's 1 red candy, which we'll say is R1, and another red candy, which is R2. Then, from this yellow candy, we can select either the first red candy or the second red candy to get the simple event of yellow, red 1, and the other simple event of yellow, red 2. If we selected the first red candy first, we can either select a yellow or a red, getting the simple events red 1, yellow, or red 1, red 2. Likewise, if we select the second red candy, we can either select yellow or the first red candy, getting the new simple events of red 2, yellow, red 2, red 1. Since these are equally likely simple events, the probability of each of these, probability of E1, is going to be 1 out of 6, and so forth. All of them are going to be 1 out of 6. There are 6 equally likely events. If I'm looking for the likelihood or the probability of getting 2 red candies, I can just look at my outcomes. These are the only outcomes where I'm getting 2 red candies, so that probability is going to be 1/6 plus 1/6, or 1/3. The last topic we'll talk about in this video is this topic of a complement. So if A is the outcome of some experiment, then how can we categorize the other outcomes? And that idea is what we call the complement of an event A, which we will primarily denote as A bar. There's a little bar over top of that. That's going to consist of all of the outcomes in an experiment in which A does not occur. It'll be the complete opposite of A. So for example, if a football team plays 16 games and wins 9 of them, find the probability that the team loses any given game. So among the 16 games they played, they win 9, which means 16 minus 9, the complete opposite, is 7. That's how many games they lose. And we're going to assume that there's no ties here. So the probability of losing is going to be the number of ways a team can lose. They've lost 7 games divided by the total number of times they've played a game, which is 16. And that's going to be the probability that a team will lose any given game. As you can see, the next section we're going to talk about in the next video is the addition and multiplication rule. This is another way to break down slightly more complicated events that are made up of multiple simple events. If you have any questions, please let me know. If not, I'll talk to you next time.